Okay. So, as everyone's aware, or hopefully aware, class has been too short, right? And we are behind schedule. So, can you see that or not? If I turn the lights slightly down, because I'm thinking it's going to be more board space. But what if I do something like that? Is that easier? And then you'll still be able to see what I write. Okay. So I'll try and be a little bit more specific about the things that we're saying here. We were talking about the first law of thermodynamics. We're talking about like work and energy and heat in a system. How going from point A to point B in this thing called PV space requires us to change components of the gas. So whether that is to change the volume, to change the pressure, those might take energy, or those might indicate a change in the temperature in the gas, right? So these are properties of the gas. And we define things like intrinsic variables and extrinsic variables. Intrinsic variables being the things that are properties of the gas, that is to say, per unit. So if you have something like the mean energy per molecule, that would be a little e versus a big E, which would be the total energy. Is that fair? Okay. So now we need to define something called, let's make sure we're all on the same page here. Hello. Okay, we can read that still. There's some more words. What is enthalpy? I'll see if I can do this. I'm gonna write H. Oh, you can write on the board. I just make sure I don't do that when the screen's down. Okay, so we're gonna define something called H, which is the enthalpy. And this is defined as E plus little p V. Okay? And what this basically means here is that, what is E again? Energy. Yeah, the internal energy, right? And what is PV when you think of them capitalized? Pressure times volume, right? So that's also a form of energy. So if you remember your ideal gas law, it goes PV equals nRT. nRT. And nRT is the thermal energy, right? That's an energy equation. This one here is the enthalpy equation, which essentially says that you have the thermal energy, okay? And here you have the pressure volume potential energy. Okay, so what does that mean? So pressure volume potential energy arises from the fact that you can, with a compressible fluid, change the volume and get energy out of the system without changing the internal temperature. Is that fair? Okay. So in practice, we take derivatives of Q. What was Q again? I write it like this over here. I write delta Q plus delta W equals. Yep, correct. And what is the last line here? Delta E. And what is this called? First law. The first law of thermodynamics. Good. And so this one was what? Heat. And this one was? Good. Okay, so in practice, we can take partial derivatives of Q we can take partial derivatives of H, and we can take partial derivatives of E. And we're going to take them with respect to T. So what does that look like? That looks like something like dQ dt. So what does that mean?
Temperature changes that quantity, so like heat will work.
Say it again.
You're seeing the change in temperature in each of those parts, like the heat that's being exchanged.
The heat that's being exchanged with respect to temperature, right? So how does the heat, the internal heat, change with respect to temperature? Does that make sense? Okay. So another way of saying this, and maybe you've seen these before in StatMech, is let's take a more common one, and it's the definition of enthalpy. Sorry, not of enthalpy, of the specific heat. So you may have seen this. So at a specific pressure, you can take a derivative of the enthalpy with respect to temperature, and you will get this specific heat. Okay. Similarly, you might say something like CV, and that's defined as the derivative, not T, with respect to V. Does that make sense? These are definitions. Okay. All we're doing in this circumstance, so let's take a look at this one, right? Cp equals the derivative of H. Remember, we wrote H up there, and we're going to keep P constant, right? So dt, this will be dE dt, and this will be a constant that'll come out, and it'll be dV dt. Okay. This is a shorthand way of writing. These are properties of the gas or of the fluid or of the liquid, right? These are things that you can derive. Is that fair? Okay. You can, in general, let's see, how do I say this properly? If we imagine, for example, that let's take this one here. And we like to play these games in thermodynamics where we set one thing that's constant, and then we do a specific type of transformation in the state. So if we imagine that it's a reversible process where the work done here is due only to PDV work. Remember what PDV work is? That is where the box is changing, the pressure and volumes are changing, right? PDV work. Okay. So the first law of thermodynamics would say that this piece here, the dE dt, is actually going to be equal to dQ dt at a constant volume. Do we see why that is? Yeah, so if you just look up here, the first law, right? The QDT and the EDT are going to be equal as long as the work done is reversible. Right? Okay. So there's no increase, right, in the work. Similarly saying we can do this with the enthalpy, and we can do this with Q as well. So we can also go over here, and we can say that you have something like dQ dt as a function of P is also the specific heat. Is that fair? This is a weird way to do class. Or do we like writing on the board? Right? Kind of helps with the notes, maybe, to see it at the same time. Yeah, so this is generally what we'll say. We'll call them specific heats at constant volume or with pressure, and these are measurable quantities. They're fluid properties. You'll find them in a table. So if you're working with water, this is something that you can just figure out. Sometimes you'll have a very easy fluid or gas. So for example, one of the easiest gases is, what's the easiest gas to work with? Hydrogen. Yeah, hydrogen is fucking simple, right? It's one proton, right? And hopefully you have an electron so that it's not a plasma. And so you have this nice, beautiful shell and it bounces around. And that's a perfectly good gas, right? We find that gas a lot in nature. And so the properties of it are very easily derivable using this wonderful thing called quantum mechanics, right? So we can use quantum mechanics to describe the ensemble of states. And it turns out that you get things like the specific heat at a constant volume and the specific heat at a constant pressure, and they fall out naturally. And they compare very well to empirical evidence, that is to say, people who just study this in a lab, right? So we always forget that this information didn't just come down on high, even though I'm sitting up here just sort of like talking. People in labs discovered it, and we had to figure out why things were that way, right? Question before we move on? Okay, second law. Oh, that's weird. Now I have to erase the board. Okay. Second law of thermodynamics is what?
Goes to a higher form of everything.
Yeah, yeah. So this is about the arrow of time, right? The simplest way, the conceptual way of thinking of the second law is that things move from an ordered state to a disordered state, or that this quantity that we're going to define as entropy always increases, okay? So you can look at the definition. So there must be a thermodynamic property known as entropy. We're going to define it as S because why don't we use E? Why don't we use E? What's E? It's the energy. So we can't use two letters for the same thing. Okay. So you could, if you really wanted to, if you wanted to be really painful to yourself, you could do this, right? And you could write, instead of an S, you could write EN. Oh shit, no, because they both start with EN. You do ENT, and you do ENE. And at that point, you're just writing the word, you're not saving yourself any time. So we use S, even though there's not an S in the word entropy. Okay. You okay with that convention? Okay, what does it mean in layman's term? What do I mean by entropy always increases? Do you have an example that you love?
Jar of marbles.
Good. What happens to a jar of marbles? Good. So another way of thinking about this, right, is that every marble, instead of being in its little jar, which is a highly ordered state, then took up all of the area that it could, right? Highly disordered state. What is that similar to? What's the difference between a gas and a liquid, by the way? Gases are compressible. Liquids are compressible. Liquids are
Unexcited.
no, they're not more excited. So we can have very unexcited gases. It's related to marbles. Marble example you just said has an analogy for gases. Liquids don't do this. That's why I can drink my liquid in that jar. It takes up the whole volume. Gases, when introduced to a new environment, take up the whole volume. So if I put my hand here and I had a whole bunch of gas in there, and then I opened it, you would all eventually sense that gas, right? So that's the idea of the gas molecules moving around, taking up as much space as they can, akin to how you dropped your marbles, right? They take up as much space as possible. Is that a good example? You like that example? You're going to use that at home? Explain to your parents? Okay, so we can write this for reversible processes in this formula. We can write TdS, or this is the entropy, is given by delta Q. Okay, so what did I say here? I essentially just said that the temperature and the change in entropy are equal to a change in, what was Q again? What? The heat, correct. So heat causes changes in temperature and entropy for reversible processes. Okay. If I combine this, for example, with our first law in reversible terms, the one that was we did at the end of class last time, which was maybe I'll just write it. There's another version that we can write dE equals. Do you remember that one? Delta Q plus delta work. For a reversible process, we just use PDV work, right? It's minus PDV, right? And we introduced this thing called the specific volume, right? So if I combine this with that, then I get something called the Gibbs energy, or the Gibbs equation for enthalpy, or entropy, sorry. So it's TdS. And now I have dQ here, I have dQ here. I'm going to put that over. So this is equal to what? dE, the change in the internal energy, plus the PDV work. Right? Or you could also write this, if you want to write it in terms of the enthalpy, which we wrote on the last page, you can kind of still see it here. H is defined as E plus PV. Right? So that's helpful because you can go between the energy and the enthalpy quite easily, whether or not you add or subtract the PDV work. So then you just write, this could also be equal to BH minus V. Okay. A lot of letters. A lot of letters. So interestingly enough, these ones here, once you combine them for reversible processes, they are also applicable for irreversible processes. How is that possible? Yeah, so this is very close to, I would change the language just slightly, but the same idea is here. And it's the idea that these are quote unquote state variables. That the path no longer matters because I got rid of work, right? The work is not present here. This has only to do with, for example, the temperature, the internal energy, and the PDV, the pressure and the volume, right? These are the state variables as opposed to the things that are changing like Q and W. Right? And so therefore they apply for reversible processes and irreversible processes alike. Okay? So you can have an example. Let's say you have very nice cold iced coffee and you have a stick or a little like spoon. Okay? And you go in here and you start stirring. What's going to happen? Oh, yeah, I want to find out less. It would melt. Why would it melt?
It's not hard, but like, the energy that you're doing to it.
Yeah, so you're doing this, you're stirring it. And are you changing the pressure? No. Are you changing the volume? No. So this piece falls away. This is clearly not a reversible process. Right? Because you're gonna watch the arrow of time, you're gonna watch the ice cubes get smaller while you're stirring. Now imagine you do this in a perfectly cold room, right? Like it's not exchanging heat with the environment. You have to imagine perfect scenarios here. But just the process of stirring it does what? You're adding heat because you're stirring. You're moving the molecules. And as you move the molecules, it causes here heat. And therefore the temperature goes up. Right? Cool. Does this process make sense? Okay. We're gonna go kind of light on like how deep we go into equations of state. What we're trying to do is we're trying to get through some of the fundamentals first. We're trying to get through statics. We're trying to get through thermodynamics. And then we can talk about how we create equations of fluid motion. And we'll bring them back in, right? So if this is your first time ever seeing thermodynamics, don't freak out. We're gonna see it again. We're gonna leave it and we're gonna come back. And in that meantime, I hope that we have discussions outside of class. If you have questions about it, I'll show you how to brush up. Okay? Let's say you took it and you didn't feel very good at it. That's perfectly fine, right? Okay. We talked about compressibility. Who said that? Okay, compressibility, right? In a compressible fluid, oh gosh, we have some new words. Let me get rid of this first. So what does it mean, a compressible fluid? Do we have any of those that you know and love? Gases, I heard is correct, right? Yeah, that one's very obvious. So for example, balloon. Take a balloon. Right? And then you compress it and then fills up the balloon. Okay, anything else? What about a compressible liquid? Anyone? Compressible liquids? No? I can't. Think of one. You can't think of one at pressures and temperatures that you're used to. Right? What?
This is the 5 year.
Yeah, I didn't say like right in this room, there's no compressible liquid in this room, that's true. But we want to think about all liquids, right? We want to think about all fluids as a whole. And so it's obviously much harder to compress liquids, and we'll talk about that. But for example, the pressure the density in the ocean, right, when you get to the bottom, is much higher. Not just the pressure, the physical density, right? Because of the pressure all the way above it. And you do have compression, right? Okay. So, okay, this is a weird word. Isentropic. What does that mean? So I'm gonna really like, especially in this class, if you've ever taken my class before, I'm a big fan of words. Right? And I gotta fucking define everything and why is he always asking me to use the right word? Okay. That'll be your main complaint, probably, other than how annoying. But how do we define this? Okay, I heard like you were brainstorming it. So walk me through the second part of the brainstorm first.
Breaking up the word.
Yeah, you broke up the word, but what was the second thing you said? Entropy? Where's the entropy? Entropic. Oh, good. So this, and let's do it like this. You guys know how to do this with words to get the roots, the etymology? So entrop, this one here is entropy. What's this piece here? IC. I know this one here. Oh, sorry, you're getting ahead of me, but you're
Property or something.
exactly of or having to do with, right? Okay, and then what's the first one? The same, right? So what we're missing here is a letter O, and this means iso means same. Okay, so what kind of variation are we talking about here?
Taking out,
Excuse me?
taking out. So the entropy, you're going to higher energy, I'm assuming this is like for batteries.
Well, interestingly enough, we haven't necessarily restricted the energy as going up. Right? So the arrow of time, I guess, do you want me to rewrite how this piece here, this is the second law. And I'm not going to write both versions, I'm just going to write the first one. It's TDS equals, remember? dE plus PdV, right? So in fact, if you think just about the ds part, right? This has two contributions. You can change the internal energy, or you can change the PdV work. And both of them will change ds. Right? So it is easy to get like, if I do this and I stir it, you see this piece. You see the heating, you say, oh, heat goes up, entropy must go up. That's not the case. Because what could I have done? Correct, exactly right. By changing the volume, I can account for the change in heat, and therefore the entropy doesn't go up. Right? Okay, so it's a battle, or it's a trade-off, right? You have one thing going up, you have one thing going down, and that will change how the entropy is perceived in the system, right? So let's go back to this word. Isentropic means entropy stays the same. So if there are changes in volume or pressure, they have to be accounted for by either change in energy or the other one. You know, for example, if the pressure changes, goes up, volume has to go down, right? Or similarly, the pressure goes up, the temperature has to go down. Internal energy, I should say, not temperature, internal energy. Ignore my words. Okay, so this is the second law. We love it. We know how to use it. Let's think about how you hear me right now. How do you hear me? With your ears, that's correct. All right. So you hear with your ears, at least most folks. How can me talk you hear, not the biology, but how space distance?
Sound waves.
Sound waves. Okay, so what's happening in my throat is that if you feel your throat while you talk, you'll notice that your vocal cords, they move. And what they do is they create waves. They compress the air and then they rarefy it. Compress the air and they rarefy it. And they send out wave fronts. And it travels to all of you out of my mouth like a little beacon. Right? If I stand this way, it bounces off the wall and still comes to me. Okay? So you have a compressible fluid that is the air. And if I create variations, because of my vocal cords, they travel at a finite speed. What's that speed? Speed of sound. Very good. Okay. Both right. What was the answer though?
I think it's 330.
330 what? Okay. So what do we use that traditionally to time? We were done so far? What? Yes, okay, so that works for the scientists, but like, let's say you're just like sitting out on your porch, you're having a little tea, it's late at night, and you hear something or you see something, and then you hear it later. What do you count in order to, number of seconds in order to know what is far away?
It's called
What are you looking for?
All the space in between, right?
What are you looking
Lightning.
for? Lightning. Right? You want to know if you're in danger. So you see a big flash, and then you count 1, 2, 3, and now you know that it's 3 times 330 meters. That's at least a kilometer away. Okay, I'm not that worried. If it's 10 seconds, you have plenty of time. If it's like, oh, you're like, oh, fuck, right? So this is like, maybe not everyone has this experience, but like, if you're from the South or you're from like East Coast, you get this all the time. There's a lot of lightning. We have less lightning. That's very sad. To go back to your point about Doppler, we can use that effect to measure, how fast things are moving, right? You could, for example, the Doppler effect is great for you watch NASCAR. All the cars come toward you and they're all high pitched and they go away. Right? Cool. We said that. How do we write the sound speed for an incompressible fluid? Well, it turns out that this is a property of the fluid. Okay. You'll show this derivation later, but I don't want to show it now because we're not doing waves yet. But it's something like this. We always say this here, c squared. This is the wave speed. And we define it as the derivative of pressure with respect to density at a constant entropy. Okay. So if I just think about that in the context of compressibility, right? So what this means is how is the pressure changing with respect to density? Right? That's how fast I can affect changes in the fluid. So let's go back to our idea of water being incompressible. If water is truly incompressible, can water propagate sound waves? No, with this formula, right? Okay. But interestingly enough, how does this work? Are mediums that have higher compressibility or lower compressibility? Let me say this without it being confusing. Take a medium like the air. Okay. And what's happening with the air is that the compressibility is pretty high. Let's say I make it more like water. Does sound travel faster or slower? Are you sure about that? Why is that? Because physics. Hold on. Let's think about our expectations here. Okay, let's think about, we always need to go back and make sure that we're remembering why it is that these molecules communicate anything. Collisions. Good. If you put the molecules closer to one another and you reduce the amount of distance that they have to bump into each other, what happens to that sound wave?
Pressures.
Well, we haven't necessarily talked, I don't want to get into the details exactly for how this works, but let's say it's just a bunch of billiard balls or something, right? If the billiard ball has to travel farther to get to the next one to push it, right? Then the wave travels slower. Because we have to remember that it's not like an individual particle of air is coming from my mouth and going in your ear. It actually doesn't get very far at all. It just bumps into the nearest one, and the wave moves faster than the particles. Right? So if you get them closer together, that wave moves even faster. Right? And in fact, you see what happens here is as the density goes to 0, the sound speed is. Well, don't think of this as the speed of light. Sorry. This is just the speed of a wave. This is heading towards what property? 1 divided by 0 is? No, infinity. Right? So as this gets smaller and smaller, this thing goes to infinity. That make sense? Okay. So for incompressible fluids, d p d rho is 0 such that c is infinity. Sorry, I said that. Happens when they both look exactly the same. D rho dp 0 such that c is infinity. Okay. Cool. Cool beans. Cool beans. Okay. Let me ask you about have you ever been on a freeway or you're going on the underpass and you see the other freeway and it looks like it's got segments? Like this freeway has different pieces and then there's a gap. So they're touching, but there's a gap. What's happening? Good. So what's happening with time? What do you mean by time? Time is going forward. You're just saying it's getting older? It's time like passes. Something very special happening as time passes. Happens every year. It's colder and it gets hotter. What happens to concrete in heat? It expands. So those gaps fill in. And during the heat of the summer, they're closer. And it's really cold the further apart. Right? They build in the expansion of the material. And in fact, because everything is made of molecules, fluids do this too. Right? So as I heat up a fluid, it will automatically expand and contract with temperature. Right? So you have something fun, you call it the thermal expansion coefficient, and it just looks like alpha. And it's defined as -1 over the density, d rho over dt at a constant pressure. Right? So if I read this, what I'm saying is, how does the density change as a function of temperature? That's of course what I'm asking. And then you just normalize it with density. Okay, and we call that the thermal expansion coefficient. And what's very cool is that if you want to measure this, how would you do this in a lab for, say, water? Sure, let's not freeze it because then it becomes a solid. We'll make it cold. I love that idea, right? You make it cold, you heat it up. You don't want it to change states, right? Because you don't want to see it undergo a thermal change. So it's maybe a more boring observation, but maybe you start at 1 degree Celsius and you go up to like 99. And all you have to do is just watch the water level and see how the water level rises or falls, right? Because it's going to take up more or less space. So they have done this for many fluids, okay? A lot of what you're going to learn in this class, and I'm just going to reiterate that, is observational. We are trying to explain something, and you'll see why this is so hard to do later, that is understanding the dynamics of individual particles is pretty straightforward. Understanding the dynamics of ensembles of millions of particles is fucking hard, okay? All right. Okay, so let's talk about what my mother never calls me, a perfect gas. What's that? Hope so, yeah. You know what I mean? What do you mean a perfect gas? I think we all know the ideal gas law, right? But are there conditions that need to be met for something to be considered an ideal gas? What are they?
It has to be exactly one element, or the same type of molecule.
I'm not sure that that's right. I might say it different. So I think I would say that they must not interact. So if, for example, you have a mixture of gases, hydrogen and helium, they can't interact with each other electronically. So they can't form bonds, they can't be mixing in a way that creates a hydrogen helium mixture that's not individual objects together. Does that make sense? So as long as there's no forces between them, then it's okay. And what is the what is the ideal gas law? How do we write that? So PV equals, and I'm just use slightly different language here. Okay. What's that? I know. I'm gonna use slightly different language. So it's gonna be N KV T. Okay. I know that's not as beautiful as the one that we have come to know and love, but it's gonna use some of the variable types that we continue to use throughout the semester. Okay, so this is what we call an equation of state. Okay, this is something that I do really want to highlight because understanding equations of state has everything to do with how we go from individual molecules to understanding how the ensemble behaves and operates. Okay. So what this means is the equation of state is what is PV equal? Right? And that's just a generalized question. Some equations of state do not depend on NKT. And they depend on other things. Like sometimes P times V to a number, the power of a number is a constant. We'll see that in a second. Okay? Sometimes they have really weird equations of state where it goes like the temperature to a power, right? So depending on whether or not these two conditions are true, that's the only time that you get the one we don't love. And almost all the other times, it's not true. So here's the first question. Are the attractive forces between molecules negligible, right? So in the air, do we think that this is true? Oh, interesting, right? It's kind of a weird question. Are the attractive forces between, what's the primary components of your air? Is there hydrogen in our air?
I'm pretty sure there is some.
Primary components.
Okay.
Nitrogen and oxygen. And by what ratios?
Oxygen's like what, like 20% of the air.
Very good. What, 22, right? Good. All right, and this is everything else. And this is N2. This is O2. Okay, and I think it's like 70 something, 76. Okay. So most of the molecules are nitrogen atoms and they are diatomic. And the oxygen atoms are diatomic. And they don't form chemical bonds with each other. So the attractive forces between the attractive forces between molecules at very large scales is negligible. Of course, we'll have modifications to that when we think about the fact, well, it is a diatomic gas. So there is some space in there that the energy is not just put into billiard balls bouncing around, but you can in fact excite both the oxygen and the nitrogen. And that allows for more states. So we talked about the fact that we could have a jar of marbles and toss them on the floor and they will immediately expand and go everywhere. But what if one of the states for marbles is not just to be on the floor, but to be rolling or to be spinning, right? If the marbles can roll or spin, they can turn energy into that rolling and spinning motion. and then they take up a different type of space. Okay, the second one, what's V? Volume, good. The volume. And what's N? Good. Okay, so this is like the specific mass, but now we're just talking about the number of molecules. The V over N has to be much larger than the average volume of a molecule. What does that mean?
Like for, you're taking sample spaces that are that small.
What do you mean by that?
Well, because I'm imagining that like you're doing, like you said, where it's negligible,
Yeah.
you're doing a big area.
Yeah, that's essentially what we're saying, right?
Okay.
Like if this thing here, V over N, the total volume divided by the number of particles gives you like an average size per particle. If that was smaller or on the same size as the size of a molecule, then they would be right next to each other. And that's clearly not a gas. They're sitting right next to each other and bouncing into each other. That's not gas. That's what? Let's say you have a lot of guys in it. What if they could do this? Come on, folks. Liquid. Liquid. Okay, when they're very close together, they're liquid. When they're far apart, they're. That's the only difference. It's when they sit in configurations that they become solid, right? Okay, so we can write, we wrote that one over here. This is equation 1.27, but we can write this a number of different ways. So I can do N over V, like that, N over V. That's the opposite of that. Okay. I can do N over V, and I can use some other lettering, and of course I can write this as P equals rho RT. Is that okay? Same equation as state. Turns out that I can define this thing R. What do we call R in English or in science? Correct. Yeah, gas constant or universal gas constant, whatever one you feel confident with. But notice that it actually has a meaning. It's just the difference between the specific heat at constant pressure and the specific heat at constant volume. So it's a property of the gas. We measure R for different gases, right? And over here, you have this other thing, Cp divided by Cv. So let's see how we get there. We're going to define that thing. And we are going to make a really, really incredible argument. Okay? We're going to say that a process is adiabatic. Wait, hold on. How do we define adiabatic first? Remember? Zero heat transfer. Okay? So something is called adiabatic if it takes place with delta Q equal to 0. Right? Okay. If a process is isentropic, remember what that means? Isentropic? What? Entropy is the same? Good. So a property is isentropic if it's both adiabatic and lacks friction. But then the entropy doesn't change. Can you see that okay? I know my handwriting. Okay, if an isentropic flow exists and you have a perfect gas, then you get this beautiful equation. P divided by rho to the power gamma equals constant. Okay. Ever seen that before? Another way you can write that, of course, is that you might have seen it this way. P and rho and minus gamma. That's the same. And now if you use any of these other versions, if you have an isentropic gas, you can relate temperatures at one period to temperatures at another. So if, for example, you have an isentropic gas and you know how it started. Let's say you know that it started with a certain pressure, certain temperature, certain volume, something like that. You only need a couple of those values in order to go from point A to point B, right? So you might say something like, here's how the pressure changes. So you could say, this leads you kind of naturally to something like T over T naught, or T naught is some starting point, is just equal to P over P naught, all to the power of gamma minus 1 divided by gamma. And I can do something similar like that. The reason why that's fun, of course, is that gamma is a property of the gas. You can measure that, right? So if you know the gas and you understand these properties, you're just plugging and chugging. You don't have to understand everything about the process to get from point A to point B, as long as you can validate that the process itself is isentropic, that it added no heat and didn't have friction. Okay. Is a car engine isentropic? No. Because why? Heat, right? Yeah, bang, 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 right? We got the start. Okay. How do we feel about this? I know we're just jamming concepts in this morning. Yeah.
That last bit, put in. Is that just like the rule itself for the empirical equation of state? Or
This piece here or
what you wrote down?
this piece here?
Yeah. Can you-
Yeah, this is only. Where did I put that? This is only for this case. Right? So if you have an isentropic gas and it's an ideal gas, then you can do this. Gotcha. And you can derive that if you want. I think we might do that for homework. But you can look at something like this. TDS. Right? So if we get rid of this side, we have something like DE, and we have an equation of state between P and rho. Easily work that out. Right? Okay. Not easily. I shouldn't say easily. It would be straightforward to work it out, even if it's not obvious. Okay. Here is a fun little. That's less helpful now because you already figured all of them out. Adiabatic, isentropic, isobaric. What does isobaric mean? Good.
That's a bear.
Yeah.
I think that's what the pressure.
Good, good. So we said IS is a prefix. That means it's the same, right? So here, this is the Greek. This is etymology. You want to start here? Adiabatic. We're going to go backwards. We're going to find out how it works. Ik is the prefix of or having to do with. That comes from English. Adiabatos means impassable in the Greek language. If you go back, you have the word batos. dia, and not through passable. Right, so they combined all these words, and if you want to go one farther back, you go to Beinin, which means go. So not through go. Okay, so when you see the word now, adiabatic, what is not going through? Heat. Right? And I want you to take a few seconds to think about this idea, because heat and fluids have a long relationship. Before we understood that they were molecules, do you know what the theory of heat was? Remember that all these theories have to come from observation, from laboratory measurements. And this has been around a long time. Greece, this is not like recent Greece. This is not 1890s Greece. This is ancient Greece.
Maybe stuff like that, keep it up,
What?
maybe stuff like that, or when they would keep stuff up, maybe.
Yeah, okay. So the relationship between fluids and heat comes from an early concept that heat was an invisible fluid that poured between containers. Because if you take a hot plate and you put a cold piece of ice on it, what appears to happen? What? It melts. The heat travels up into the ice and melts it. So people thought that heat was a thing that moved from point A to point B like a fluid. And therefore, an object was adiabatic if it did not allow that fluid to flow in. Right? Isn't that wild? Fucking words, bro. All right. Questions, comments, concerns? Okay, we're gonna go longer because I have you till 45, even though it doesn't say it on the schedule. And we'll talk about in the last 15 minutes or the last 5 minutes, we'll talk about we're gonna make up that hour. Okay. Adiabatic process take place without the addition of heat. I added a cute bat because it's cute. Frictionless processes are called isentropic. We figured that out, right? We love that. And we talked about this equation. I already deleted it, but it's this one. That's a constant property of the gas if it's isentropic. So if one, then two. What does an adiabat look like in PD space? What was that? Yeah,
Yeah.
it's pretty good. That's pretty good. Is this an adiabat? No. What is that change? What? Good, but what is that change? We have a lot of words that we're gonna throw in, and we're all gonna use like these like ISA. What would this one be?
Take out.
Is the pressure constant or the volume constant? Volume is constant. So even though the change is in a pressure, we call it an my favorite one to do. This is an iso volumetric change. What? What the fuck? All right, what about this one? Now you're gonna get this one, right? What's this one?
Isobaric.
That was easy, right? Isobaric. So now can we connect them like this? Is that normal?
I
Is it?
think you have to curve it, right?
Yeah, you wanna go like this one?
Yeah.
So let's see if that works. Lower pressure, lower volume. To higher pressure, higher. volume.
But then,
You'd have to add heat, so that's definitely not an adiabatic process, right? So if I connect them like this. Doesn't matter what the shape is, right? If I do this. I've added heat. Okay, what about this?
that's okay.
That's what?
Okay.
Why is it okay?
Otherwise, even though the pressure's going down here, it's compensating for.
That's this here, right? So we can say that it's adiabatic as long as ds doesn't change, right? That means that either dE doesn't change or that PVV work balances. We happy? Or like marginal? Okay. What does sound speed and thermal expansion depend on? Yeah. So if we think about it depends on the density, it depends on the pressure, it depends on the temperature. We wrote it down a few seconds ago. Not quite the entropy, especially not for an adiabat. What is the equation? Yeah. So let's have a look at the c squared is defined as what? Good. At what? We like that. And we said that this is an adiabat, an isotropic process. So in fact, we can write this, huh? Interesting, very interesting. So P can be related to rho, and we can take a derivative if we wanted to. Oh, maybe that would make a good homework assignment. So I could put in here rho to the gamma times a constant. And I could do the derivative, right? As long as it's an adiabatic isotropic process. And I can say this thing. Right. No one's rebelling yet? You have a question?
I mean,
You want me to do it? Because I'm gonna maybe make you do it. You want me to do it? No, you can do that derivative.
well, I can't really think of it.
Okay, so that's the derivative of rho gamma. Question make sense? What is it?
Yeah, more bro. Yeah.
C gamma
Bro. Okay.
right? So now we can directly derive the sound speed. And what did we use? We used the density of the gas and the properties of the fluid. If I increase the density of the gas, what happens to the speed? Bing, bada, boom, right? What did we say earlier? You put the molecules closer to each other, speeds up. It's not gobbledygook, it works. And as long as we can do the derivatives confidently, we can make it give us answers that make sense. Now, what do we have to be careful for, and what are we absolutely gonna mess up a bunch of times before we get it right? Making sure our assumptions are valid. Because even though we look at something like this and we say, oh, I understand this, we might have it exactly backwards, right? We might think, oh, the thing's changing in pressure, it must be isobaric. No, that's not what that means, it's isovolumetric. Similarly, if I go from here to here, it's certainly not an adiabatic or an isentropic process. Okay, almost there. That says stability of a stratified fluid. So what you're seeing here is in a static fluid potential, gravity's down, rho, which is the density, P, which is the pressure, and T, which is the temperature, can vary with height. That's pretty standard, right? Okay. Give me an example of where this happens. In the audience.
Water towers,
Good. What happens in a water tower?
the pressure of the water from the height is enough to give us the pressure at the bottom.
Exactly, right? So the column of water at the very top, the pressure is almost nothing. At the bottom, it's very tall. Right? Very tall, very big. Good. Anywhere else? Too bad. Okay. My question is, where do you see, either in your daily life or in nature, a situation where there's a static fluid and rho, which is the density, P and T might be vertically stratified. That is to say, they change with height. A balloon, a helium balloon? Yeah, let's think just of one fluid right now, because otherwise, because that's going to be in a bath of other fluid, and then there's going to be buoyancy forces that we haven't discussed yet. What? Is a waterfall a static fluid? No, not because of the static part, right?
So maybe the water towers they use for the farm supply?
You just said that. That's good. I'm glad that folks are thinking similarly. That means like you're on the same wavelength.
Well, when you flush a toilet, that force is just from the, right?
Okay, let's go again. What? The air. The air is vertically stratified, right? If I go to a mountain, what happens? Yeah, no, breathe good. I keep going, die. Big die. Right? Open window on plane, not a good choice. Right? Why is that? No, yeah. I'm fine. Not the plane. Why is it that the pressure at altitude is low? Okay, that is the definition of the pressure. But why for is the pressure low? What is the reason for the season? Pressure. The stuff above it. And therefore, in a vertically stratified system, gravity pointing down, the more stuff you have above it, the more pressure, the more temperature, the more density, right? Where's the warmest part of the atmosphere? What?
Like sea level.
Sea level, right? Now, of course, this is an idealization. We haven't talked about chemistry, we haven't talked about any type of physics, right? In an ideal gas that's not moving, the hottest part is the bottom. All of the stuff above it. Good. So here is our beautiful isentropic curve. Here's density, okay? And the density is going to change as I go up. As I move a parcel of gas from a point called Z naught, and I bring it up some distance psi. Right? You want to learn how to draw that? It's pretty fun. It's like this. Oh, shit, I didn't do it right. Imagine that I drew it really good. Like I always do all my drawings. Psi, okay? So you have some parcel of fluid and you bring it up, raise it up. You have an elevator for some fluid for some reason. And you don't let it get heated. Right? So what happens to this parcel of fluid? Volume changes to compensate, right? And maybe the parcel of fluid is now steeper than the isentropic fluid. So let's imagine that for a second. Steeper, by the way, is more up and down. Shallower is more left, right. So here, this claims that rho d, the density at this point, being larger than the density at this point, right, means that it's unstable. So if I bring this parcel and it's more dense than C, what will happen? What's that? Let's just think about the gas particle. Okay, so let's say I take a balloon of gas. And the volume here at sea level is whatever it is. Okay, and now I take it up 30 feet. And I do it quickly enough or I do it smoothly enough that it doesn't have time to exchange properties with the surroundings. It doesn't come to equilibrium yet. And now I compare it to the gas nearby. And the particle that I brought up has density C, and it is smaller than the surrounding gas. Now what happens to that parcel of gas?
Kind of like oil and water, it's gonna go underneath
Which one is going to go underneath which?
the denser one, it's gonna go.
Denser one always goes underneath, right? So if I bring up a parcel of gas, a balloon of gas, and it's, down here, it's whatever it is, but by the time that it makes it up here, it's moving isentropically, so its density has reduced, but it's reduced, say, more than the surrounding gas. What happens to that parcel of gas? Gonna keep going. So if I take a parcel of gas down here and I isentropically bring it up to a region where the atmosphere itself is still denser than an isentropic particle would be coming up that far, now it hasn't reached equilibrium, and so therefore it keeps moving. That's why we call this steeper curve an unstable atmosphere. It's unstable to convection. What I mean by that, and I'm going to show you this in a few seconds, is it's not going to turn over and send that parcel back down. Parcels that move up isentropically leave. right? Now, of course, we're gonna get into fluid dynamics and you have to replace that parcel and everything else, but we're not talking about that yet. Currently, what we're talking about is the ability to move up here and then out. If that same parcel moves up to C, and now it's heavier than its surroundings, here, B, then of course it sinks and heads back down. That is called convection. Okay? Okay. Okay, so we ran out of time, but I think we finally got through like a sizable portion. Did it feel like that class was like more full? Like we actually learned some stuff today? So here's the thing I realized. You're owed about an hour of class. So I am thinking that I'm just gonna do that. And probably record it, because I don't know that I can force you to be here in person. Unless you want to go an extra 15 minutes every class, but I think that's kind of insane. So here's what I'm gonna do. I'm going to do two things. I'm gonna record a lecture for you. I'm gonna post it on what we call the YouTubes. Has everyone found the YouTubes? And then I'm gonna give you homework 1. And even though it's not stuff that we've done in class and will require you to watch that homework or watch that extra lecture, I think by forcing you to see that homework and be expected to do it, I think that'll be better, right? And we'll use some of the concepts. So instead of just seeing all this bullshit at once, like, oh, I can do these derivatives, right? Comments, questions, concerns? Yeah. Yeah, we will start homework 2. Because homework 1 was sending photos, right? And the videos that you took of your cool stuff that you found. Do you find cool stuff? Okay. And everyone else saw the thing that you got added to the you got added to Slack, and you saw my poll about whether or not you can make office hours. Because if you don't tell me that you can't make any of my office hours, then I won't be able to add more office hours.